So previously we have learned that the change of magnetic flux through a closed loop will induce an EMF and an induced current in the loop. Okay, change of magnetic flux causes EMF and current to be flowing if there is a loop. So the way it induces an EMF and induces a current can be explained by Faraday's law and Lenz's law. So Faraday's law states that the induced EMF is equals to the negative of the time rate of change of the magnetic flux linkage, which you can break it down into the number of turns times the magnetic flux. And the magnetic flux can be further broken down based on our understanding that it is a dot product of the magnetic field and the area vector. So the magnetic flux is BA cos theta. If it's magnetic flux linkage, you multiply it with the number of turns. Then you get MBA cos theta. So you can bring in the MBA cos theta into the magnetic flux linkage. And at the end, you arrive at this form of equation where the induced EMF is equals to the negative number of turns times the time rate of change of BA cos theta. So based on this equation over here, we know that either one of these value can change with time will cause a change in magnetic flux. So it can be the magnetic field change with time that will cause a change of magnetic flux. It can be the change of the area experiencing the magnetic field. There will be a change of magnetic flux. Or it can be a change of theta, a change of the orientation of the loop causing change of magnetic flux. So there's three ways to cause a change of magnetic flux in order to induce an EMF and induce a current. Okay, so down here we have explained three different methods. The first method is to change the magnetic field strength. So the magnetic field strength, you can change it, then you keep the number of turns, the area constant. You also does not rotate the loop. So the N and the A and the theta are all constant. You can bring it out from the differentiation. So what's left in the differentiation is just the magnetic field strength, B. So that's the first way, by changing the magnetic field strength. The second way of doing things is by changing the area of the loop that is experiencing magnetic field. So in this case, you will bring out the B and the theta because you're keeping the magnetic field strength constant and you're not changing the orientation of the loop. So the B and the theta will be constant. And in this case, I'm putting it as there's no Bn here, means by this is a single loop. Okay, you can add on the N inside if you have multiple loop. Okay, let's add on an N inside. Okay, so if you can also change the area, you can also think of another situation as changing area. And the situation is if you have a moving straight wire, means by you're swiping a straight wire through a uniform magnetic field. So when you're swiping a wire through a uniform magnetic field, you can imagine an imaginary loop, and from there you can think of the situation as a changing area situation. So for this situation here, there will be no number of turns because it's just a single wire. So you can think of it as a single imaginary loop. So the N here will automatically become 1. So it will be B cos theta, but the area here, you're going to change it into length times width. So the length will be the length of the conductor, and the width here will be changing with time, representing the change of area as the wire swipe across the magnetic field. So the width is the one that is changing with time. So if you have an imaginary loop, you have to determine whether the area is changing, increasing or decreasing in order to substitute in the correct sign for your velocity here. So the change of width with time will be replaced by the speed over here, but you have to put in a positive or negative based on whether the area here is increasing or decreasing. Okay, so we remove the cos theta and all the angle if the magnetic field, the length of the wire, and the velocity are all perpendicular to each other. If they're all perpendicular to each other, then all the theta we will not put it into the equation. It will just be BLV. Okay, so for this situation, it can be positive, it can be negative based on the speed that you put in here, whether it's causing the area to increase or causing the area to decrease. Okay, third method of doing things is by changing the orientation of the coil. So you can rotate the coil at a certain frequency or you can rotate the coil, you can change the angle of the coil with respect to the magnetic field. So when you do that, the magnetic field strength does not change, the area of the coil does not change, the number of turns of the coil does not change, so you can bring all this out. What is changing here is the data over here. Okay, so if you differentiate it with time, you have to change this, you have to change the data here to become omega t. Okay, data be replaced by omega t, and from there you can write your equation as MBA omega sine omega t. Okay, cos differentiate here will become negative sign. That's why you cancel with this negative in front. That's why there's no negative sign over here. And this omega t here can also be replaceable with data. It depends on how you use the equation. Okay, and for this kind of situation, this kind of rotation question, they can also ask for the maximum induced EMF. And if it's maximum induced EMF, you know that sine omega t here will have to be equals to 1 in order to maximize EMF. So it becomes MBA omega. Okay, so these are 3 different methods of changing a magnetic flux. And for changing area, there's 2 different situations you can analyze. So that describes everything regarding Faraday's law. And the Lenz law is represented by this negative here, because this negative here is trying to say that it's to indicate that the induced EMF and the induced current is in the direction to oppose the change of magnetic flux. Okay, so you can review that in the Lenz law video.